Okay, let's make sure we've got audio here. It looks like it's coming in. Okay, so put this down out of our way. Okay, find a periodic sequence, all the periodic recurrence sequences. So let's just focus on the case where the two roots of the quadratic are distinct. And so the theorem tells us that un is of this form, c1 lambda 1 to the n power plus c2 lambda 2 to the n power. And now put in this recurrence. Okay, so set them equal, and you should be able to end up with an equation like this. We've got lambda 1 to the n times some value a plus lambda 2 to the n times some value b equals 0, where capital A is something and capital B is something. And then you want to deduce from this that capital A and capital B are 0, if this is true for all n, for all natural numbers n. So get capital A equal capital B equals 0. And then you know what capital A and capital B are in your calculations. So you'll have something like C1 lambda 1 to the k minus 1 is 0. And C2 lambda 2 to the k minus 1 is 0. So lambda 1 and lambda 2 have to be kth roots of unity, if they appear at all. Of course, if C1 is 0, there is no lambda 1 to worry about. So lambda 1, these are the only cases that are really we have to think about. So we have to ask, what are the possible kth roots of unity we can have? And these lambda i's satisfy a quadratic equation. So the lambda i's are satisfying a quadratic equation. Okay, I didn't specify what setting we're working in here. Okay. Right. So I didn't specify whether we're over the rationals or over the reals. So if we just want periodic sequences, I guess we could just let lambda i's just be any kth roots of unity in the complex numbers. If we did have a stipulation that I wanted these to be sequences with rational values for A and B in recurrence, then I'd have to ask, when can kth roots of unity belong to a quadratic extension of the rationals? And that's a little more difficult question. Okay, and then you'll have a case 2 where lambda 1 equals lambda 2 to think about. Moving on. Part A is a straightforward common denominator. I see a little typo right here. And then part B, if we just substitute in what this equals, so substitute that in, and I'll just mention one word and move on. Okay, problem 3. Use part B of the preceding problem to prove this limit exists. So this limit is the limit of that series. And what was that series? Negative 1 to the k plus 1, fk plus 1. So what are we looking at? This is an alternating sum, and so all you need to remember is the alternating series test. You have an alternating series like this, so AK, and how does the test go? You need two conditions. The AK need to be decreasing, and the second thing is the AKs need to be going to 0 as k goes to infinity. And that implies the series converges. So just apply that test. And then for part B, prove the limit of the sequence is the golden ratio using only this fact. So if we use that fact, I'm going to just divide both sides by Fn. One plus, and look at what we get over here. These are reciprocals of each other. And so just call this limit L up here and solve for L. Take the limit of both sides and solve for L, and we should get the golden ratio, which I see a typo right there. Square root of 5 plus 1 over 2. Need to go back and correct those. Okay, number 4. Use this matrix and formula for a geometric sum. So A and B are very similar, so let's just look at this one right here. And so we have to keep in mind our formula for the a to the n power being fn minus 1, fn, fn plus 1. That. So if we, instead of looking at this, we look at this sum here, I'll pull off an A. And the 1 is the I is the identity matrix. And then normally when we write a geometric sum, we would go like this. Of course, that's an abuse of notation. Abusive notation. But it helps us remember how this works. What are we really looking at there? You're talking about the inverse of some matrix in the denominator. So you have A minus I inverse times A to the n minus I, like that. And now just calculate it. You know how to find the inverse of a 2 by 2 matrix. So you just calculate that and then just multiply it out. And you should get something where this term here is going to pop up. And so you just paste it together. And then look at the left side. The left side, you will have a matrix with, let's just focus on its entry up here. You'll have an F1 up there. And when you square it, you'll have an F2. And when you take it to the nth power, you would have an Fn. So if we just follow what's going on in the upper right corner when I add these matrices, we will get the sum of the Fibonacci numbers. And you can probably focus on any one of the entries, but that one is an example. Problem 5. What's the sum of the Fibonacci numbers appearing in one cycle mod M? So we've got F0, F1, F2, Fk minus 1, and then Fk. So let's say the Pisano period is K. So at this point, Fk equals F0, etc., etc. So one period is this sum right there. Mod M, and I don't think, unless you haven't looked at problem 4, It's time now to look at problem 4 because there is a formula for the sum of consecutive Fibonacci numbers. So if you just come back to problem 4, this one should come out really quick. Number 6. Show that if P is a prime with P congruent to plus or minus 1 mod 5, then P is a divisor of Fp minus 1. Okay, so this should suggest the theorem we did on these periods. So I said if P is congruent to plus or minus 1 mod 5, then pi of P is a divisor of P minus 1. Okay, so again, just think of the sequence of Fibonacci numbers. So this is a theorem in the notes. And you get out here where you hit Fk. So K is, let's say, the Pisano period. All right. So what can we say? So here's the Pisano period. And what is the value of this? Well, what can you tell me about Fk? Well, Fk is congruent to F0. That's where you get the repetition in the Fibonacci sequence. And F0 is, of course, 0. So P seems to be a divisor of Fk. Okay, now there's two ways you can proceed. You can either think about periodicity, or you could use this fact that if D divides N, then the dth Fibonacci number divides the nth Fibonacci number. So put those two things together. And then there's a similar argument for the P congruent to plus or minus 3 mod 5. Let's see, part B. Prove that every prime is a divisor of infinitely many. And it's the same thing. You can either use the periodicity again, or this fact here. It should just pop out immediately. Zeckendorf's theorem is very interesting. Every positive integer can be uniquely expressed as a sum of distinct Fibonacci numbers, no two of which are consecutive. And of course, it's obvious why we don't want them consecutive. If you had two consecutive numbers, you would combine them and get the next number in the list. Okay, so there's an existence and uniqueness part to this. So we're going to use the strong form of induction. And do both the existence and uniqueness simultaneously. Okay, so well, you can get yourself going on a base case. So the inductive assumption that we're really going to focus on is this. We suppose the statement is true for all positive integers smaller than n. Suppose true. Strictly less than n. And then let's consider the value n. Okay, so consider the positive integer n, and I want to show it can be expressed as a sum of one or more distinct Fibonacci numbers, no two of which are consecutive. So let's draw a number line. Like this. And just as a quick hint, this problem is going to be a little more lengthy. I just thought it was interesting. Some of you may want to pursue it. So here is n. And the natural thing to do if you're trying to express it as a sum of Fibonacci numbers is to find the largest Fibonacci number, say right here. Let's call it fk. That's less than or equal to n. And then we would have maybe fk minus 1 right here. And so the next Fibonacci number would be over to the right of n. So I'm going to let fk be largest Fibonacci number less than or equal to n. And I'll consider two cases. The first case is where fk is strictly less than n. And then we'll look at this little difference here. Let's call that m. So let's let m be n minus fk. And note that's strictly less than fk plus 1 minus fk. But what does that equal? That's fk minus 1. That's the recurrence relation for the Fibonacci sequence. So this difference m is strictly smaller than fk minus 1. So by induction assumption, m has a unique representation as unique blah, 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 as a sum of one or more distinct Fibonacci numbers, no two of which are consecutive. And moreover, because it's smaller than fk minus 1, with no fk or fk minus 1 in the representation. Now come back to n, and you're going to get n as a sum. So the question then is the uniqueness part there. So that's existence. And then uniqueness, you'd make a claim that if n equals some like this of distinct non-consecutive Fibonacci numbers in descending order, then this one here must be fk, and fk must occur in the sum. So fk, remember, is the biggest Fibonacci number smaller than n. Why must it occur in the sum? Well, if not, the biggest sum you could form is what? Biggest sum of non-consecutive Fibonacci numbers so it would be we'd have to start with fk minus 1, and then go to fk minus 3, and then go down to, and you're going to either end at what? F2, so I would end there if k minus 1 is even. And if it was odd, I would end at F3 because the stipulation in our problem is that F1 is not permitted. So you'd have to stop at F3. And that would be if k minus 1 is odd. And a claim, you have to go back to the earlier problem on sums of Fibonacci numbers, of consecutive Fibonacci numbers. Both of these are equal to fk minus 1. And I get a contradiction. Okay, I think I've said enough on that one. Problem 8. Draw a rectangle. Okay, the part 1 is just proof by picture. And remember, this is just motivating the identity, so you don't have to write a real rigorous proof in part 1. The rigorous proof is part 2. So you just want to indicate how would one go about breaking up this rectangle. And it's kind of the self-evident. You just partition off a square here, fn by fn squared, and then you partition off, well, what's this length right here. So you calculate that length, then you partition off the square here, etc. Part 2 is just standard induction proof. You'll have your base case, n equals 1, and then the standard induction assumption. I don't think there's any fancy thing going on. Assume true for n. So you'd have this statement is true, and then you would add an fn plus 1 squared to both sides, and it should be pretty standard induction proof. So I can talk to you more about that if you need more experience. I think in the appendix to the notes, I've got some standard induction proofs if you need to review that concept. Fibonacci number test. Okay, a quick warning on this. This one is a little more involved, but it's an interesting problem. It gives you a test for when a natural number is a Fibonacci number. So it's a Fibonacci number if and only if 5n squared plus 1 or 5n squared minus 1 is a perfect square. So what we have to do is work in this ring. So I'm going to let phi be the golden ratio. And I'm going to work in Z phi, which is the set of all linear combinations with A, B, and Z. All right, so you have to work in this ring. And we need one fact about it, that the units here in Z phi are just powers of V. So they're objects of this form, plus or minus phi to the n power, where n is an integer. Right? I mean, you can easily see that these are units. Why are those units? If we use our delta function, delta is the square of the absolute value. You can quickly get that. On this thing right here, it's 1 minus 5 over 4 is negative 1. So you can quickly see that phi is a unit. And therefore every power of phi is a unit. The converse is a little deeper result that let's just assume right for now. So, okay, so we've got, these are the units, and that's just background. Okay, so now what you want to do is take the formula for the Fibonacci sequence, And let me write phi bar for the conjugate quantity 1 minus root 5 over 2. It's not the complex conjugate, but that notation is easier to work with. And notice that phi times phi bar is the constant term in the quadratic. That's equal to -1, or you can just multiply it out. And so this is 1 over root 5 phi to the n minus 1 over phi to the n with a negative sign. And so we get a quadratic equation where you can solve for phi to the n in terms of f of n. So use the quadratic formula. And you get that phi to the n power is negative root 5 fn plus or minus square root of 5 fn squared minus 4 times -1 to the n all over 2. And now you're seeing that test right here, that 5n squared plus 1, or 5n squared minus 1. I've got a 4 here. We want that 4. Let me see. Ah, that was a typo again. Typo. Okay. Hopefully, whatever version you're looking at, I can put in those corrections. So now you're seeing the connection here between this answer and this thing underneath here. Well, okay, so there's two directions then. On the one hand, we are trying to show that if n is a Fibonacci number, then this is a perfect square right here. So now you go ahead and consider the directions explicitly. We want to show that this quantity underneath here is a perfect square. Minus this is a perfect square. So what you do is you say, well, this is equal to phi to the n power. Now, phi to the n power is an element of z phi. So phi to the n power is the element of z phi. So let's say phi to the n power equals the a plus b phi, or better yet, let's put it in this form, c plus d root 5 over 2 for some integers c and d. And now set this equal to this thing right here. So on the left-hand side, you're going to have c plus d root 5 over 2 equals that. Do some simplification and prove to me that this has to be a perfect square. Okay, so that's one direction. Then for the converse, what do I want to do? I want to suppose that I'm given an integer such that 5m squared plus or minus 1 something like this equals a perfect square. Well, if that's true, that's going to imply that your delta applied to this type of object like this is going to equal plus or minus 1, which means this is a unit. But we said, oh, the units are powers of the golden ratio. So that's going to tell us that a plus root 5m over 2 is some power of this golden ratio. And then the conjugate would be a power of the conjugate of the golden ratio. And if you add those two things together, we should be able to get a formula, solve for m, and show that it coincides with a Fibonacci number. Because we know the formula for the Fibonacci numbers. All right, well, there's some hints. You can play with that if you want to enjoy that problem. Number 10, prove this is true. Try a proof using the matrix A. So again, it's just the fact that a to the n power is fn minus 1, fn plus 1 that we want to use here. And so think about what fn squared plus this looks like. So a to the 2n plus 1. No, let's not even do that. A to the 2n. Calculate it two ways. So on the one hand, use formula directly. So this equals blah, 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 blah. On the other hand, you can actually calculate a matrix product over here and just equate the appropriate entry. Number 11. Deduce from the previous problem that every odd-numbered Fibonacci number is the hypotenuse of a right triangle. So this would be your f2n minus 1, where the legs are 2fn, fn minus 1, like that. And it's just a matter of plugging it into the Pythagorean formula. I don't think there's anything else that's going to go on, and using this relationship right here, fn squared plus fn minus 1 squared. So I think there's probably nothing more that I would really need to write that down. So you just show directly that when you multiply this out, just want to verify that identity. Okay, that's it. So what do I do?